Firstly, I think I should admit that yesterday it seems that on one count I failed miserably. So it is on which count? That is the following. So what is the agenda? What am I doing? First of all, yesterday the entire effort were really on introducing the concept of freedom model. So I have a sister algebra A. A freedom model is given by a pair. We know what they are. It's a inverse space. If it is a self-adjoint operator, the square is identity. And then we also have this condition. If commutator pi A, or instead of pi A, I will often write just A. This is a compact operator, but this happens for a dense. Oh no, this happens for all A. This can happen for all A. So this is for all A. If I further demand that this is inside some Chapin ideal B1 or BP, then I will have some other on some dense algebras. I use same symbol A infinity, whether it is 1 or P, then such a thing is called P sample. So our goal was introducing that, but just to introduce, we started with this remark of phenomenon that we do not understand anything, we get used to, so we will get used to, and sort of I wanted to tell you why was it necessary to introduce. Otherwise in mathematics often one introduces concepts, plays with them without telling you why was it absolutely necessary. I remember our calculus course which was done on Banach spaces, multivariate calculus, without a single word uttered or why was it necessary. So we learned all those things, but it was not really told in the class why one must learn calculus in Banach spaces. There are some binding reasons. In this case, of course, the reason is not really binding, but since we go to college, first numbers we learn groups, and so this looks like a very natural question that gamma is a discrete group, torsion free, then whether C gamma or C star gamma has no non-trivial projections. Since we are looking at groups for quite some time, we feel that yes, this is the question which we must answer, and therefore attempts to answer that sort of leads to this. And of course, yeah, we will see its answer for another specific groups, but as one makes these groups more complicated, this machinery also has to be kind of enriched appropriately so that one can employ this to answer this question. So then we learn a simple lemma which goes as follows, which was really simple. So if I have something like the following, so let tau be a faithful trace on a sister algebra A such that tau of a projection is, of course, it is within this, and we also know this, then that implies P equal to 0 or 1.
And by trace
here by trace I mean faithful tracial state, it is really as in the sister algebra formulation.
Tracial state.
Yeah, fine. Maybe I should emphasize it is a tracial state. So that means it is a positive linear functional on A. Yeah, thanks for pointing out, because I was using this word trace with another meaning, and that was the following. So if I have something like this, then I can define a functional again I am using same symbol, half trace gamma f computer A. This is just a linear functional here. It satisfies this, and tau of B actually solves the counting problem. We saw it last time that there is an operator which has got finite dimensional kernel and co-kernel. It is the difference between those dimensions, therefore it solves the counting problem. Therefore this one is actually in Z.
Partha, there is one question there. F computer A
Yes.
is in trace class for only a set of
Exactly. So that is a good point. That is a good point. So let us see how to kind of extend this, but that is a good point. A priori, just from this argument, we can conclude this only for the dense subalgebra A infinity. So how do we do it for A? So is this question clear? As he is saying, this makes sense only for a dense subalgebra A infinity. Therefore, I can use this argument only for the dense subalgebra. How do I extend it for the whole system algebra? That is the question. Sort of, meaning I cannot quite really argue. So first of all, we are looking at projections in this algebra matrices over A infinity, and then a group is constructed out of that. And there is a, so what is this map? If P belongs to Mn of A infinity, the projection, then I can think of P as a projection in Mn of A as well. Therefore, that gives a map, and this is really some group produced out of these objects. So that gives a map from here to here. And now, using that, okay, fast. Flow is disturbed, so I'll come back. First, let me give an example of this. You will see that in this example, this tau actually can be defined as a trace on the whole system algebra. So,
Positive?
yes. Yes. But only thing you do not know is about solving this problem. Only thing you do not know is that. So, tau solves this problem.
You may be able to extend it as a state, but it won't look like the one you started with.
No, that is not necessary anymore. That is not necessary anymore. That is simply because. So I will be able to extend this tau.
So this tau has
Let me finish. Please follow, and then you can follow it entirely. So this tau extends as a trace. Therefore, what happens is, given any trace, I have a function going from here to, namely I compute tau tensor ordinary matrix trace of that projection. So I have a function.
What is that?
K0 infinity is a group produced out of K0
What's the subscript? What's the subscript?
Zero. So the group produced out of it, using the tau I produce a homomorphism from here to here, and this map actually gives an isomorphism. And again, using that same tau, I can produce a homomorphism that shows given any projection P, this quantity, which is defined using that trace, is actually Z.
Good to give the example.
Example again. So let us do it. Example will be slightly tricky. So let us again think of it quite abstractly. This is an object. It is isomorphic with that. So what does that mean? I did not give you the inverse map, I only gave one-way map. So the trick is really in the inverse map. So you start with a P here. As it is isomorphic, that means it is really of this form. And therefore, if you hit by tau, it is same as this quantity is same as kind of result of applying tau here.
So the isomorphism exists separately.
Isomorphism exists separately, and so that is being used. So without that isomorphism, you cannot. So this is not really a complete argument, because of course anyway you cannot do complete arguments. Yes.
What about positivity? The two you defined
Yes.
is highly non-positive.
There are two taus, so I should yeah. So 1 second.
No, but
So let me give you a tau. I have not given any H or F. How do you know it is non-positive? I have not specified it.
I'm asking.
So let me
You have given it out.
No.
It is highly non-positive.
No, that is quite symbolic. If you have H and F, you have a tau. But it begins with if you have an H and F. Starting with your group, what is your H, what is your F? I have not specified, therefore let us do that. Therefore let us do that. Once you do that, it will be kind of immediate that why is it so. So let us now at this time begin with gamma equal to. After all these are really quite general discussion, just to introduce the notion in that generality. So gamma is free group on this two generators bit is not really important. So I say gamma acts on a tree. So what is a tree? That is gamma and this is T. So what is a tree? Tree consists of two objects. There is a vertex set. It is really a special complex. So there is a vertex set, and vertex set is really elements of the group gamma. And there is an edge set. So what is an edge set of a tree? Edge set of a tree is really a collection of pairs of vertices. So we say so two generators